Hi everyone, I'm Gautam Kumar from Google, and today I'm going to present Swift. And through our paper and this presentation, I aim to convince all of you that Swift is simple and effective for congestion control in the data center. So, what is Swift? In one line, albeit a long one, Swift is a delay based congestion control for data centers that achieves low latency, high utilization, and near zero loss, implemented completely at end hosts, supporting diverse workloads including large scale incast across latency sensitive, byte, and IOPS intensive applications, working seamlessly in heterogeneous data centers with minimal switch support. The highlighted keywords here summarize the requirements for an effective and deployable congestion control at scale. Swift achieves near 50 microsecond stale latency for short flows while maintaining near 100% utilization even at 100 Gbps line rate. So the question is, why did we build a new congestion control for data centers at Google? We talk about this in detail in the paper. I'm going to summarize three key reasons here. First, we have new applications with low latency requirements. Flash needs 100 microseconds of access latency at 100K plus IOPS. NVMe needs 10 microseconds of access latency at 1 million plus IOPS. We have large scale incast, which is typical of partition aggregate workloads, and we have IOP intensive applications, for example, the BigQuery shuffle operation. We have new networking stacks such as Pony Express, which is built atop Snap, and we published Snap at SOSP of last year. And these exhibit congestion behavior which is no longer limited to the fabric. For example, in the case of Pony Express, endpoint congestion is key because it is built for CPU efficiency and is non-interrupt based stack. Third, increasing line rates. We now have 100 Gbps networking and beyond. And what this means is that we need fast reaction to congestion because the queue buildup happens very quickly. Additionally, congestion control needs to be robust to heterogeneity. Tying congestion control to switch internals has posed a maintenance burden. Let me briefly summarize some of the conclusions from our experiences as we deployed Swift fleet-wide at Google. First, delay works really well. The use of delay as a multi-bit congestion signal has proven extremely effective for excellent performance, for robustness, for simplicity, which has helped greatly with some of the operational challenges. Second, fabric and host congestion are both important to respond to. And initially we underestimated, like most designs do, this aspect. But what we realized that both forms matter across a range of workloads. And what is nice about delay is that it is decomposable to separate concerns, to handle fabric congestion as well as host or endpoint congestion. And handling both fabric and endpoint congestion is also important for end-to-end performance of applications. Finally, we have a wide range of workloads, including but not limited to large-scale incast. And what we have realized is that always-on pacing is not needed to support large-scale incast. Think thousands of flows. And Swift is built in a way which is CPU efficient. So we pace when we need to, and we don't pace when we don't need to. Let me briefly summarize some of the key aspects of Swift's design. We present the detailed design in the paper. I'm going to highlight some of the key aspects, and I'm going to talk in a bit more detail one of the aspects, that of how Swift handles fabric and endpoint congestion separately. Swift uses both hardware and software timestamps not just to measure the delay accurately, but to also be able to decompose it. The details of how we do timestamping, what are the packet header changes that are needed, how do we measure the delays, and how do we decompose them are all in the paper. The main idea behind Swift is very simple. It is a simple additive increase, multiplicative decrease, which is applied on a CVIND maintained in packets based on a target delay. So if the observed delay is less than the target, we increase the CVIND additively. Otherwise, we decrease the CVIND multiplicatively. Swift is able to seamlessly transition between C1 and RAID. And this is needed to handle large scale incast, as I was just referring to. Because to handle large scale incast, think not hundreds of flows, but thousands of flows. We need to allow the C1 to fall below 1. And how we implement C1 below 1 in Swift is via pacing the packet using a timing wheel. But we do not pace the packet when the C1 is above 1. And what we have found is that always on pacing is not needed to achieve excellent performance. And this aspect of Swift's design aids CPU efficiency. Next, the target delay used in Swift is not static. We scale it dynamically based on topology because network distances are well known in the data center, and this provides RTT fairness. Additionally, we also do flow-based scaling of the target delay. The details are in the paper, but the idea here is that we need to account for queuing that occurs because of chance collisions. And to handle that, what we do is we provide a slightly higher target to smaller events. And this part of Swift's design helps with both fairness and convergence. Happily, we have not needed to invest much in loss recovery because losses in Swift are, well, extremely rare. We use selective acknowledgement to aid fast recovery. And we also have an RTO mechanism to ensure data delivery when we cannot use fast recovery. As an example, let's say when the ACKs get lost. Swift is deployed at Google fleet-wide in a shared deployment, which means that we have WAN traffic, which is using its own CC. We have cloud customers, which are using the CC of their choice. And to provide isolation for Swift traffic, we leverage COS features in switches. These COS features are readily available in all commercial switches. Most of them support 10 plus COS queues. And what we do is reserve a subset of them solely for Swift traffic. Let me go into a bit more detail into one of the aspects of Swift's design, which is to deal with fabric and endpoint congestion separately. So let's consider this diagram which shows the end-to-end delay decomposition of a packet and its ACK. So we have a local endpoint which sends out the packet and a remote endpoint which processes the packet and sends out the ACK back. So the packet first spends some time in the local NIC queue. It then goes through the fabric, arrives at the remote NIC. It waits for some time before it is processed by the remote stack. Then there is some processing delay involved, which is the time that it takes to generate the ACK. The ACK itself sits in the remote NIC queue. Then it goes through the fabric. Eventually, it comes to the local endpoint and waits in the NIC queue before it is processed by the local endpoint. So here, through the use of hardware and software components, we are able to measure these delays. And which delays to react to, it depends on the details of the stack. So for example, you don't need to react to local NIC RX delay if the TX and RX scheduling at the local endpoint is separate. And what we do is that we measure the fabric delay and the endpoint delay, and we maintain two congestion windows, one for the fabric and one for the endpoint based on their respective target delays. And the effective congestion window is the minimum of these two. With this background on Swift's design, let's briefly discuss some of the production results from our fleet-wide deployment of Swift at Google. We present quite a few production results in the paper. Here I would highlight a few of them. We present the detailed methodology and how we collect the data via switch counters and other means in the paper. One thing I would note here is that the main point of comparison for the production results presented here is GCN, which is a DCTCP style congestion control algorithm deployed at Google. So the first metric of interest is loss rate, and here we are showing both the average and the tail loss rate at the 99.9th percentile, um, first versus port utilization from 0 to 100%. And we have bucketed the port utilization in range of 10%. Uh, and we also show both the average and the 99.9th percentile loss rate versus cluster utilization or cluster throughput. We are providing the normalized loss rate numbers here uh, because of confidentiality reasons, but we'll provide some absolute numbers through our testbed evaluations. Um, the key takeaways here are that Swift is able to keep the loss rate very small uh, at the average and at the tail at the 99.9th percentile while running near line rate utilization. And another thing to note is that the improvement in loss rate for Swift does not come at the expense of throughput. As we can see, that Swift is able to sustain the same cluster throughput as GCN. Uh, and while we have normalized the absolute production numbers for confidentiality, I would like to note that the GCN loss rates have been an operational challenge in production. Let's talk about latency. So in this plot, we are showing the CDF of the Fabric RTT, both for GCN and for Swift. And the green vertical line here is the value of the base target delay. Note that this is just the base value of the target delay, that is the static part, and does not include the dynamic parts which depend on the topology and flow-based scaling that we perform on the target. And the takeaways here are that Fabric RTT with Swift is significantly smaller than GCN, especially so at the tail. And secondly, the target delay as a tuning parameter works really well, as we can see that the achieved RTT is close to the configured target. It does go above the base target here, but note that this is the base value of the target delay and not the scaled dynamic value of the target delay. To understand how well the use of COS queues in switches works to provide isolation that is needed for Swift traffic in shared deployments, in this plot we are showing the normalized loss rate for Swift on the lowest priority COS queue and for GCN on the strict priority COS queue. And the takeaway is that the use of COS works extremely well in providing the needed isolation for Swift traffic from non-Swift traffic in the shared infrastructure such as Google. And what is interesting is that the Swift loss rate on the lowest priority COS queue is actually lower than the GCN loss rate on strict priority COS. Finally, to see how important endpoint congestion is in production, we are showing the CDF of the RTT and the NIC delay for a throughput intensive cluster and for an IOPS intensive cluster. We can see that for the throughput intensive cluster, the NIC delay is one of the components of the endpoint delays. We can see that for the throughput intensive cluster, the NIC delay is not a big part of the round trip time. Whereas for the IOPS intensive cluster, the NIC delay is actually a big portion of the round trip time. And what this shows is that endpoint congestion is, uh, is, is important to react to, specifically so for IOPS intensive workloads. We actually have quite a few additional production results in the paper, including some interesting production experiences. So I would encourage you all to go through them. Uh, let's briefly discuss the testbed evaluation we perform. And the goal of our evaluation is to study the microscopic behavior of Swift. Once again, we have extensive evaluation in the paper. I'm only going to highlight a few of the results in this presentation. The first is that Swift is able to precisely control the delay as per the target delay. And to show this, we run an experiment with 100 to 1 incast. The line rate here is 50 Gbps, and we are varying the target delay from 10 microseconds to 70 microseconds on the x-axis, and we are measuring the achieved RTT and the throughput. And what we observe is that Swift is able to precisely control the achieved average RTT to be around the target. We also note that a very small value of target delay hurts utilization. So target delay needs to be selected properly. We also show the load latency profile of Swift, uh, and the line rate in this experiment is 100 Gbps. And what we do is we vary the load from 0 to 100%, and we measure the achieved RTT and the achieved throughput, and we show that Swift achieves consistently low RTTs while maintaining the throughput. To understand the impact of Cwin less than 1, where we pace packets when the congestion window falls below 1 using timing wheel, how important is that to handle large-scale incast, we do an experiment with 5000 to 1 incast, and we compare Swift and Swift without Cwin 1, where we take away the support for Cwin less than 1 from Swift. And what we observe is that Swift in this 5000 to 1 incast is able to achieve line rate throughput, almost zero loss, and very small RTT. Whereas if we were to take out the Cwin less than 1 support, we observe high RTTs, a loss rate of 28.7%, which drives the throughput down to just 8.7 Gbps. So the takeaway is that the Cwin less than 1 support is extremely effective to deal with large-scale incast. To see how Swift performs on the yardsticks of fairness and convergence, I'm going to present two experiments. In the first experiment, we start with one flow and we incrementally add flows one by one and then tear them down one by one again. The line rate in this experiment is 50 Gbps, and what we see is that Swift is able to quickly converge to the correct fair share rate as flows come and go. To see how Swift works and to see how Swift works in fairness in large scale incast, so not in the simplistic setting, but under extremely large scale incast, for example, thousands of flows, we do an experiment with 5000 to 1 incast and see that Swift achieves a Jan's fairness index of 0.1 and achieves pretty good fairness across flows. And this in part is aided through flow-based scaling. For if we were to take out flow-based scaling from Swift, the Jan's fairness index drops to 0.78 and we do not achieve as good fairness as we do with it. As I mentioned, we actually have quite a few more. We have quite a few more experiments in the paper, and I would encourage you all to go through them. I would like to conclude and point out some interesting future work here. So to conclude, what our experience has shown is that surprisingly, complex constructs for congestion control in the data center are largely unnecessary. Using delay as a congestion signal, we can realize a very simple congestion control that achieves excellent performance for data center workloads. I'd like to call out some of the future work in this area that can be fruitful. Transport agnostic and highly portable congestion control for public clouds. We can also use delay for higher level primitives. For example, doing control at higher level operations such as RPCs or RMAs. And finally, to achieve ultra low latency, less than 10 microseconds for short transfers that is close to the propagation delay in the presence of bandwidth intensive transfers. Thank you.